Well, welcome again to our journey into algebra and number theory, and we've been looking at quadratic reciprocity. And so I'm going to now give a little lemma, and then I'm going to state what the quadratic reciprocity theorem is all about. Gauss regarded this quadratic reciprocity theorem as one of his greatest achievements. In fact, he gave two different proofs, in fact probably more than two different proofs of it, but the proof presented here is not one of them. It's a curious fact that many proofs of this theorem, some of them essentially the same, have been given. The proof I'm going to give is not the one you find in most textbooks. That's the one due to Eisenstein. You can look at my video on journey into analytic number theory, and I've got that proof is recorded there. This is a slightly different one. But again, it's going to be using Gauss's lemma. Now, before we do that, we have a little first lemma before we state and prove the quadratic reciprocity theorem. We take a to be a positive integer, p and q odd primes, and with p is congruent to plus or minus q mod 4a. So under that assumption, then the Legendre symbol a over p takes the same value as the Legendre symbol a over q. Now here I'm only going to prove the case where p and q are congruent to each other modulo 4a, and then you can look at the case where p is congruent to minus q mod 4a. The proof is similar. So we're going to write my p, I'm going to divide it by 4a and get a remainder of r, and r must be strictly bigger than 0 since p is prime, but less than what I'm dividing by. I'm going to use Gauss's lemma to find the Legendre symbol a over p. And to do that, we're going to consider, as usual, we take the set from 1 up to p minus 1 over 2, multiply by a, and we're going to reduce these numbers down modulo p. When we do reduce the modulo p, then those are numbers in S that are greater than p minus 1 over 2. That's to give us the k in Gauss's lemma. These will be those numbers in the intervals between p over 2, 2p over 2, and then 3p over 2, 4p over 2, and so on, where we take an odd multiple of p over 2 up to the next. So we get up to the next multiple of p over 2. Now, we're going to, dividing by a, we see that the k in Gauss's lemma then is exactly the same is exactly the number of integers in the set from 1, 2 up to p minus 1 over 2 that lie in these intervals. So I'm just dividing each of the intervals by a, and we're looking for the number of integers in each of these intervals, and we keep going until we reach the time when we're back to where we start from. So with that then, I'm going to now simply take my p. We said p was congruent, we're writing our p as 4a j plus r, so we're dividing our p by 4a and plugging that into those intervals that we just had, and simplifying we end up with these intervals. Now the parity, so we're looking at the number of integers in each of these intervals. The parity of the k is not going to be changed if we simply add or subtract even integers from the endpoints. That is, I can subtract these off. And so modulo 2, these intervals simply become r over a, r over 2a, and so on. 3r, r over 2a, and so on. Now, since p and q are congruent, since p is congruent to q mod 4a, which was our first assumption, if we repeated the whole argument again with q in place of p, then we would arrive at exactly the same intervals as we got here, since they're independent of p. Hence, the number of integers in S modulo p that are greater than p minus 1 over 2 equals modulo 2, the number of integers in S mod q greater than q minus 1 over 2, and hence by Gauss's lemma, the Legendre symbol A over P is the same as the Legendre symbol A over Q. And you can do the other case similarly. Finally, we can state and give a quick proof of the quadratic reciprocity theorem, which Gauss was very proud of and which is very important. There are generalizations of the quadratic reciprocity theorem that were done fairly soon afterwards. There's cubic reciprocity and biquadratic reciprocity, and then you get general reciprocity theorems as well, leading up to Artan's theorem, which is one of the most general ways of viewing these things, but it becomes quite sophisticated. Anyway, here, if P and Q are odd primes, then if P or Q is 1 mod 4, either of them is 1 mod 4, then the Legendre symbol P over Q is the same as Legendre symbol Q over P. That is, we can just flip the primes upside down and the Legendre symbols are the same. That only works in the case where either P or Q is 1 mod 4. In the case where they're both 3 mod 4, then the Legendre symbol P over Q is minus the Legendre symbol Q over P. Another way of saying this is if either P or Q is 1 mod 4, then P is a square mod Q if and only if Q is a square mod P. But if P and Q are both 3 mod 4, then P is a square mod Q if and only if Q is not a square mod P. Another way of one can combine these together, and I leave you to simply check the conditions on this that they actually make sense. So you can write P over Q as Q over P times minus 1 to the P minus 1 over 2, Q minus 1 over 2. The point being is if both P and Q are 1 mod 4, then these numbers are even, and then we simply get straight equality. And if both of these are 3 mod 4, then this will be an odd power up here, and we get the second one. So this is just a shorthand, cute way of combining the two of these facts together. Okay, the proof goes a little bit like this. So take P and Q are both odd, then that means P is plus or minus Q mod 4. I'm only going to prove the case where P is congruent to Q modulo 4, and the case P is minus Q mod 4, you chase through and you'll find it finishes off the proof. But it's done in a similar way. So Q over P then is, because these are, I'm going to write Q, I'm going to assume Q is bigger than P without loss of generality, and I can write Q then as P plus 4A because they're congruent. P is congruent to Q modulo 4. So I can replace the Q with this here, and we can simplify this and get 4A, and the 4 is already a square, so that's A over P. Similarly, Q over P is Q minus 4A on Q. This is minus 4A on Q, Legendre symbol. You can get rid of the 4, and this is minus 1 over Q, A over Q. Now the lemma we had then says that these two are equal to each other, since P is congruent to Q mod 4A, and that means P over Q is minus 1 over Q, Q over P. And this one we can deal with because we know that if Q is 1 mod 4, this is 1, and if it's 3 mod 4, then this is minus 1. And that gives me one of the part of the cases listed above. So as I said, the right hand side is just Q over P. If Q and hence P is 1 mod 4, and it's minus that if they're both of that form. And the other case is done in a similar way. Well, we should have a look at some examples here. So as an example, I'm going to evaluate, find the question here, I'm going to evaluate, to show you how useful this is, we're going to evaluate 359 on 617. So here's the calculation for this one. So we're going to simply calculate this one. We just notice over the side here that 359 is 3 mod 4. This is a prime, and 647 is prime, and that's 3 mod 4 as well. So what we'd like to do is we want to invert these two. So we flip it upside down, and because these are both 3 mod 4, the penalty is that you pick up a minus sign. The advantage now is that I can read 647 modulo 359 and I get 288. Now 288, of course, you immediately recognise as 2 times 144, so I can split this up as we've done in earlier examples. And of course 144 is a square, so that's 1. So this just becomes minus 2 on 359, and we had a formula for how to calculate 2 over p. It was just p squared minus 1 over 8, minus 1 to that power, and you calculate this, you find you just get minus 1. And so that tells me that 350, going back to the original problem, 359 then is not a square modulo 647. But one of the key steps in this was to be able to invert. In other examples, you have to keep inverting and inverting until you get down to something fairly simple. As another example of using this is I'm going to ask the question, is x squared plus 6x minus 5 congruent to 0 modulo 127, is this soluble? So can we find solutions to this modulo 127? Well, we complete the square on the quadratic, and I can rewrite that then as x plus 3 squared is congruent to 14 modulo 127. And so I want to know, so this will have solutions if and only if 14 is a square mod 127, and so I look at the Legendre symbol 14 on 127. Now 127 is prime, but 14 is not, of course, so I can factor this. I can use the formula for 2 over p, so it's minus 1 to the 127 squared minus 1 over 8, and that turns out to give you 1. So that's 7 on 127. Now we apply quadratic reciprocity, so I can flip everything upside down. These are both primes, and they're both 3 mod 4 primes, and so I pick up a minus sign. I can then read 127 modulo 7, and I just get 1, and so the answer to this is minus 1, and that means this equation up here, so 14 is not a square mod 127, so this equation here has no solution. Another type of example is to looking at other further Diophantine equations, is to look at this equation, x squared minus 43y squared is 73, and to see whether to show in fact that this so-called Pell-type equation has no solutions. So if they exist, if there were solutions to this, then they will still exist when I read the equation mod 43, and that will get rid of this term. So if it has solutions, then that means x squared is congruent to 73 mod 43 has solutions, and that's true if and only if 73 is a square modulo 43. So again, we look at the Legendre symbol, 73 on 43. I can read 73 mod 43 and get 30. 30, of course, factorizes as 2, 3 times and 5. Now the 2 we can deal with because I just work out 43 squared minus 1 over 8 and raise minus 1 to that power, and I get 1. That leaves me with these two numbers, and again I'm going to apply quadratic reciprocity now to these. These are now all primes. This is a 3 mod 4 prime. This is a 1 mod, this is a 3 mod 4 prime. So when I, this one here turned out to be minus 1. This turned out to be minus 1. These are both 3 mod 4 primes. When you flip them, you pick up another minus sign, so you get 2 minuses here to give you a plus. This one is 1 mod 4, so that doesn't change. You can flip it upside down without penalty. Reading this modulo 3, I just get 1. Reading this modulo 5, I get 3. 1 over 3 Legendre symbol is 1, and 3 over 5, now I can just use Euler, and that gives me minus 1. So that means x squared is congruent to 73 mod 43 has no solutions, and that means this original equation there has no solutions. Final example on this one here is to, we've already seen that 2 over p, the Legendre symbol 2 over p, is 1 if and only if p is plus or minus 1 mod 8. 2 is a quadratic residue modulo p if and only if p is 1 mod 8. What about primes for which 3 is a quadratic residue? Well, in that case we need 3 over p to be 1, and we need to look at two cases here. Because 3 is obviously 3 mod 4, we have to look at the case if p is 1 mod 4, then I can flip this upside down, and if I then use Euler, I simply get p, and that means p is congruent to 1 mod 4 to flip it upside down. Sorry, I get minus 1, I should say. So I get minus 1 then if p is 3 mod 12. I'm sorry, I've got myself confused here with this. Sorry, this one is going to be equal to 1 if p is 1 mod 4, and it's minus 1 if p is 3 mod 4. Also by Euler, p over 3 is just p mod 3. So we require either p is 1 mod 4 and p is 1 mod 3, or p is minus 1 mod 4 and minus 1 mod 3. And we can combine those together and get p is plus or minus 1 modulo 12. So there is a little proof and some applications of the quadratic reciprocity theorem.